Log on, tune in, find out. Another good idea from Cambridge.
Thank you, and I would like to thank you, the organizers, as well, for inviting me. And it's been a great week being here with so many friends and such interesting talks. So, yeah, my topic today will be the rationality of conic bundles. I should turn this on. Can you hear me? Yes. So my topic today is the rationality of conic bundles via a categorical criterion, basically, right? So let's start. Maybe can I turn this off? Yeah. Well. Okay. Seems I can't find the. Good. Okay, let's start by making a small recap of what happens to finite threefolds with negative Kodaira dimensions. We will assume that V is a smooth irreducible projective threefold over the complex field, and then by the minimal model program, and V is birational to X, to an algebraic variety X, with at most terminal singularities of one of these three types. So either X is a minimal Q final variety, or X is a minimal Delpezzo vibration, or X is a minimal conic bundle over a normal surface. And up to birational equivalence, we can assume that both X and S are non-singular and projective. Right. So we're talking about varieties with negative Kodaira dimensions, so it makes sense to wonder about the rationality of such varieties. And this talk will be about the rationality of the third kind of variety. So we will assume that X is a standard conic bundle over a smooth rational projected surface, and in such cases one can have a discriminant divisor, which is a curve contained in the surface, and a double cover associated to the conic bundle. That is the double cover given by connected components of degenerate conics. This is kind of a drawing of the situation. Singular conics decompose in connected components. You take the double cover associated to such construction. And Jx will be the intermediate Jacobian of the conic bundle. So there are some quite easy, reasonable, necessary conditions. Of course, the base surface must be rational. And more subtle, like the connectedness of the discriminant locus. This is due to Artin and Manford, because if it is not connected, one has some two torsion in the H3 of the conic bundle, and this implies irrationality of the total space. And a final condition, necessary condition for the rationality of the conic bundle is that the intermediate Jacobian should split as the direct sum of Jacobians of a smooth projected curve. So two of the highlights of the theory of rational conic bundles are due to Arnaud, who is in the audience, by the way, and Shokuro. And they say that first, the intermediate Jacobian is isomorphic to the prime variety of the double cover that I just described before. And second, which is more a criterion than a theorem, is that if S is minimal, then X is rational if and only if the intermediate Jacobian splits in such a way. Right. This gives only a few possible cases where, for S minimal, where the conic bundle is rational. For instance, if S is P2, then C may be a cubic curve, a quartic curve, or a quintic curve, and the double cover is induced by an even theta characteristic. In fact, if the theta characteristic is odd, we're in the case of the conic bundle induced by a smooth cubic threefold, which is not rational. On the other hand, if S is a ruled surface, then the discriminant locus may be trigonal or hyperelliptic, and the trigonal or hyperelliptic linear system is induced by the ruling of the Hitzelsberg surface. These are the only cases over a rational minimal surface where the conic bundle is rational. So the question we wanted to ask is a question that roots back into the origins of the theory of derived categories. Derived categories, among the reasons for which derived categories were introduced, is the birational geometry of algebraic variety. And the question we asked is, can we relate the bounded derived category of a conic bundle to its rationality? And up to now, the most promising way of doing such a thing has been by studying semi-orthogonal decomposition of the bounded derived category. I quickly recall what is semi-orthogonal decomposition. If T is a linear triangulated category, then a semi-orthogonal decomposition, it is an ordered collection from right to left of subcategories that generate, in a certain sense, the whole category. And the orthogonality is given by the morphism inside the category T. So it's quite simple. It's quite a simple idea. And recently, this example has been developed by my co-author Bernard Dara, Emanuele Macri, Paolo Stellari, and Mechrota. And it is the example of the smooth cubic threefold. If X is a smooth cubic threefold, then its derived category has such a semi-orthogonal decomposition. And there is a categorical Torelli somehow, that is the equivalence class of the category T, which is orthogonal to the rest of the sequence, corresponds to the isomorphism class of the intermediate Jacobian. And a nice remark, is that both the subcategory T and the Jacobian are undecomposable. And since the indecomposability of the Jacobian is a reason for which the cubic threefold is not rational, it seems that we are going the right way. So the idea is that the rationality of conic bundle may be connected or equivalent even to admitting a certain semi-orthogonal decomposition. In fact, let me describe briefly, before we go into the main theorems, what are the derived categories of conic bundle and how do they decompose. This theory has been developed recently by Kuznetsov, who has developed a full theory of derived category of quadratic fibrations. So if X is a conic bundle over S, and B0 is the sheaf of even parts of the Clifford algebra associated to the conic bundle, then the derived category of the conic bundle has quite a simple decomposition in terms of the derived category of the base surface. Well, in this case, it is a surface, maybe even a high dimensional variety, and the derived category of B0 algebras. So that's all, up to two fully factorial functors. So basically, you have something that comes from the base, and the rest of the derived category, the information, geometrical information that comes from this derived category, is contained in the derived category of B0 algebras. In particular, in our case, the base is rational, and a rational surface has a very simple semi-orthogonal decomposition that is in exceptional objects. This means that the derived category of a conic bundle of a rational surface has such a decomposition, and these exceptional objects are basically, an exceptional object generates a subcategory which is equivalent to the derived category of the point. So it is nothing very relevant from the geometrical point of view. So we see that most geometric information in the case of a conic bundle of a rational surface is contained in this subcategory of B0 algebras. In fact, this is what happens. These are the two main theorems. Suppose that there are fully faithful functors and smooth projective curves gamma e such that there exists, in fact, this functor to the category of B0 algebras, and a semi-orthogonal decomposition where there are also some other exceptional objects, then the intermediate Jacobian splits this way. So from a semi-orthogonal decomposition of the derived category of B0 algebras, we obtain a decomposition of the intermediate Jacobian. And then by using the criterion by Sokurov, we can say more, that if S is minimal, then X is rational, and of course the Jacobian splits if and only if the derived category of B0 algebras has a semi-orthogonal decomposition like this one. Okay, so first I will try to give a sketch of a proof of the left to right implication. That is, I will show that if we have such a semi-orthogonal decomposition of the category of B0 algebras, then the Jacobian decomposes. So I suppose that there exists a fully faithful functor from the derived category of a curve gamma to the derived category of B0 algebras. And I will study the map that this functor psi induces on the Jacobian part of the motive of the curve gamma. So I suppose that it is fully faithful, and then by a well-known result by Orloff, it is a Fourier-Mukai, since dB0 is contained in the derived category of X. And it admits a right adjoint, which is also Fourier-Mukai. So I will fix some notation, and I will call E and F the kernels of these functors and of its right adjoint. And of course, the composition of these two functors is the identity. Then I want to work on the rational Chow group, and I want to translate the information of semi-orthogonal decomposition and Fourier-Mukai functors into something in the rational Chow ring. The tool that I use to do so is basically Grothendieck-Riemann-Roch theorem. In fact, I defined two mixed cycles this way, where this is the Chern character and these are the top classes of this. And Grothendieck-Riemann-Roch in particular says that this diagram commutes. It is a commutative diagram, where the vertical arrows are obtained by taking the Chern character. So what I get here is there is a functorial correspondence between Fourier-Mukai functors in the derived categories and correspondences in the Chow ring. In particular, this diagram and the fact that composition of functors is the identity implies that the semi-orthogonal decomposition that I assumed translates into a decomposition of the rational Chow ring. So Grothendieck-Riemann-Roch implies that the Chow ring decomposes in the Chow rings of the smooth projective curves gamma I plus a finite number of copies of Q. Okay. Now I want to spend a few words on the motive of on the Chow motive of a smooth projective curve. In fact, I mean, make fun. In fact, the Chow motive of a smooth projective curve decomposes in three parts. Two parts which are discrete, that is a unit motive and a Tate motive, which are discrete in the sense that the underlying topological space of this part is just a point. And the H1 part, which corresponds to the Jacobian of the curve up to isogenies. This means that the morphisms between these two motives are equal to the morphism between the rational Jacobians of the curves. And in particular, the full subcategory of Chow motives whose objects are direct summands of the H1 is equivalent to the category of abelian subvarieties of the Jacobian up to isogeny. And moreover, no non-trivial map from H1 to H1 can factor through a discrete motive. So this is quite clear. I mean, yeah.
Do I need to know what H1 of gamma means at this point?
Sorry?
Do we need to know what this H1 of gamma is?
Well, all you really need to know is this, that, okay, you don't have a non-trivial maps factoring by the Tate motive.
An object in the category of motives.
Thank you, Mark.
Okay, so as we have seen, exactly as in the case of the Chow ring, there is a functorial correspondence between Fourier-Mukai and motivic maps. That is, the cycles E and F induce maps of this type on the motive. And always by Grothinger-Riemann rock, we have the composition of these correspondences of this motivic map are the identity on the motive of the curve. Okay, so now I need to use this result by Nagel and Saito that have studied recently the motive of a conic bundle. In fact, they showed that if S is rational, then the motive of a conic bundle is a direct sum of a finite number of copies of discrete motives, this kind, and a submotive of the H1 of C tilde, where C tilde is the double cover, which corresponds to the prime variety. So basically there is only one component which is non-discrete in the motive of a conic bundle over a rational surface. So this means that the motivic map obtained functorially by the Fourier-Mukai the Fourier-Mukai functors imply that the H1 of gamma must be a direct sum of this non-discrete part of the motive of a conic bundle. And in particular, that via the argument that I showed before, that we have an isogeny between the Jacobian of gamma and a subvariety of the intermediate Jacobian up to isogeny. Okay. And moreover, by the decomposition of the motive of the conic bundle, we find that the composition of the two mixed cycles is 0. So let me call Fi and Ei the purely icodimensional part of these mixed cycles, and that the composition is 0 unless I is equal to 2. So the isogeny turns out to be the algebraic morphism given by the two codimensional part of the Chern character of the kernel of the Fourier-Mukai functor. So up to now we only have an isogeny between the Jacobian of the curve and the intermediate Jacobian. In order to show that is an injection, that is an injection, one has to show that the principal polarization of the intermediate Jacobian pulls back to the principal polarization of the Jacobian of a curve, and this is feasible. This is just a computation that uses the fact that the intermediate Jacobian carries the incidence polarization, since it is the algebraic representative of the algebraically trivial part of the Chow ring. Okay, so this implies that it's not just an isogeny what we have. It is exactly an isomorphism between the Jacobian of the curve gamma and a principally polarized abelian subvariety of the intermediate Jacobian. So now consider, yes, this semi-orthogonal decomposition that was stated in the hypothesis. Then, as we have seen, each functor psi I gives a morphism from the Jacobian of gamma I to the intermediate Jacobian of X. And this gives such a decomposition for the rational Chow ring. That is, it decomposes as the direct sum of the Picard varieties, rational Picard varieties gamma I, plus a finite number of copies of Q. So we are close to the end, because now we want to check how it works, the projection of this decomposition of the Chow ring on the two codimensional part of the Chow ring, exactly. In fact, we have that psi q is an embedding in here, and the co-kernel is a finite dimensional Q vector space by the decomposition of the Chow ring. But on the other hand, psi is a morphism of abelian variety. So the co-kernel cannot be but trivial, and psi, it is an isomorphism of principally polarized abelian varieties. That is what we wanted to show. Of course, if S is minimal as a corollary, via the Shokuro criterion, we have that if the derived category of B0 algebra admits a decomposition like this one on the blackboard on my back, then X is rational, and the intermediate Jacobian decomposes that way. So what we have shown so far is that if dBs_B0 has such a decomposition, then the conic bundle is rational. In the remaining time, I will show how each rational conic bundle induces such a decomposition on its derived category of B0 algebras. Exactly. So I will assume that X is rational, that is, X belongs to the list I gave at the beginning of my talk, that is either a cubic plane or quartic plane curve, etc., etc. Then, in this case, we have that semi-orthogonal decomposition. So, the point is that we have to find a way to check this for all rational conic bundle, okay? But there is this exact sequence that gives us some help. In fact, this is the Brouwer group of the surface, this is the Brouwer group of the function field of the surface, and this space parameterizes cyclic extensions of the function field of curves D contained in the base surface. And if S is rational, then its Brouwer group is trivial, and the map alpha is injective. The map alpha is pretty helpful in our case because B0, the sheaf of even parts of Clifford algebra, is a two-torsion point of the Brouwer group of the function field. It is a quaternion algebra. And the map alpha basically sends B0 onto the double cover induced by the generate conics. That is the discriminant double cover of the degeneracy locus. Well, of course, you can see it as a cyclic extension of the function field of the discriminant locus. Okay, this is quite clear. So the point is that since this is 0, this is injective, and this means that once we fix the degeneration locus, the discriminant curve, and its double cover, then the algebra, the sheaf of B0, the sheaf B0 is completely determined, and of course also the category of B0 algebra. Okay, so now all we have to do is compute explicitly this semi-orthogonal decomposition for each discriminant curve and each double cover. In general, philosophically, what we do is the following. So X over S is the conic bundle, and Z is a smooth projective rational threefold with a known and easy semi-orthogonal decomposition. What we do is try to construct the conic bundle by giving an explicit linear system on Z that contains a curve gamma in its base locus, and explicit linear system which is resolved to X by blowing up the curve gamma. Yes, so in this way we obtain two different decompositions, semi-orthogonal decomposition for the derived category of the conic bundle. The first one is the one that comes from the results of Kuznetsov. You recognize it here, and this one comes from the fact that let me go back. As we have shown, the total space of the conic bundle comes as a blow-up of Z. And there is this result by Orlov that describes the derived category of a blow-up as gives a semi-orthogonal decomposition for the derived category of the blow-up in terms of the derived category of the base and the derived category of the locus along which we blow up. And we compare this different decomposition by mutation, and this is a table that summarizes briefly the case that we obtain. So here I browse through all the cases of rational conic bundles with different degeneration curve, and here are the results that I obtain. In the case of plane curves, if C is a plane quintic, then I blow up Z along a genus 5 curve, and this probably was already described by Iskovsky. But then one obtains the composition of this derived category in terms of one exceptional object and the derived category of gamma. In the case of the plane quartic, then one blows up as a quadric threefold, smooth quadric threefold along a genus 2 curve and obtain a similar decomposition of the derived category. the case of the cubic curve in P2 is particularly simple because we don't even need to blow it up. We just have a P1 bundle over P2 and a decomposition of dBs B0 in terms of three exceptional objects. And then in the case of Hirzebruch surface, the main tool that we use is Resilla's trigonal construction. In fact, in the case of the trigonal degeneracy locus, we use exactly this because we find a P2 bundle over P1 and a tetragonal curve which is trigonally related to this one. And by blowing this up, we get a decomposition of the derived category in terms of the derived category of gamma plus two exceptional objects. In the case of hyperelliptic degeneration, what we use is degeneration of the trigonal construction. In fact, it is the case where the tetragonal curve splits in the direct sum of two hyperelliptic curves, which are the ones that appear in the semi-orthogonal decomposition. And basically, one first blows up one of the two hyperelliptic curve and then blows down a ruled surface, obtaining a quadric bundle over P1. And then it blows up the second hyperelliptic curve to get finally the conic bundle X. And this is the final decomposition of the derived category of B0 algebras that one obtains. So this is the second part of the proof. That is, I checked that in all cases where the conic bundle is rational, then the derived category of B0 algebras has such a decomposition. And so the proof of the theorem is complete. Thank you for your attention.
Questions? Apparently not. So, thanks, Michele, once more.